Okay. Today might be a little bit shorter of a kind of lecture, but I do want to work through some more linear regression stuff, and we'll review some stuff we've talked about in the past. Do a little more work in Excel, and then look at a paper. So there should be on Canvas under Files. I dropped a couple papers, so oh, here, Gambler's Fallacy, G. We'll take a look at that one. I put this major choice paper on there. We'll take a look at that. And then I think I put this powerlifting data set. So we'll kind of look at two papers and then kind of work through some Excel stuff and kind of hit a bunch of points here. So I'll start with this major choice one because we left off last class and I thought that it was within the paper and it was actually a completely separate paper. But it kind of has, once again, kind of written out for us this idea of they were giving a letter to students at Montana State post, after the year 2012, right? And so they wanted to see how did that, receiving that letter kind of impact these different behaviors by the students, right? Taking more credit hours, taking less loans out. So here specifically, they want to look at, well, how does it change the probability that they choose certain majors or they switch into certain majors? So it's kind of a 1 if they switch into those majors, 0 if not. So here was kind of their results, presenting that coefficient that was, the effect of receiving that letter. So if they receive the letter, the probability that they changed majors, right, goes up by 0.02, or there's about a 2% more likely they changed majors after receiving this letter. Right? They kind of try to look for differences in high, low GPA students, and not a huge kind of difference there. It looks like maybe lower GPA students were more likely to switch than higher GPA students. Notice here, just kind of we talked about before, 3 stars means that you can reject the null, which the null always starts out, we assume that these coefficients are equal to 0. So we can reject that this is equal to 0 in this scenario at the 10, 5, and 1% significance levels. For high GPA students, we can't say that has any effect, right? There, at least at the 10, 5, and 1% levels, there's no stars indicating that the p-value must be greater than 0.1. Okay. I thought the more, so they did try to break this kind of down by freshman, non-freshman too. You can kind of think about, maybe freshmen would be more likely to switch, right? Or say in the reverse order. Seniors are probably less likely to switch majors because they had to hang around a lot longer, right? So they actually did find that for freshmen, if you just singled out the freshman students, that effect was a little bit higher, right? 0.03 instead of 0.02. And I think it's kind of interesting to look across the majors as well. So people were more likely, right, we have 1 star here, but still at the 90% level, the 10% significance level, were more likely to change major or switch major into business, less likely to switch into some of the health fields, and they have no significant effects on the other 2. But if we look down here at the freshmen, you kind of notice the probability that they switch into business is pretty high, quite a bit higher than all students. They're also way less likely to switch into liberal arts and more likely to switch into kind of the science, something classified as a hard science, right, or the sciences. So I think it was kind of interesting to look at how even just sending a letter is, changing like someone's behavior here. Here specifically student behavior, but it could be, if it was a different example, like just changing behavior with these, just providing people with information about the choices that they're making. Okay. And then, there was some, if we want to break freshmen down even further, it looked like maybe the lower GPA kind of freshmen were more likely to switch into business. Higher GPA for some reason were more likely to switch into sciences here, but it didn't kind of converge. So, some interesting results, and kind of this is the table that I was kind of mentioning and looking for at the end of last class. So it was a completely different paper. So the next paper I want to look at and kind of work through and talk through and kind of show you some results that maybe I could show you like on an exam. So we could kind of go through, usually read the abstract first, get an idea about what this paper is about. But we've actually already talked about what this paper is about. Right? So this paper is going to start to look at something called the gambler's fallacy. Right? So I think I might have, depending on the context, we've got this gambler's or this hot hand fallacy. So the hot hand fallacy is that if you see something happen, right? So if you see a success, you think a success is more likely on the next trial. Right? Well, the gambler's fallacy is kind of the opposite, where you say, if I see something happen, see a success, I think that because of the law of that, I think, oh, well, the next one's got to be a failure. Right? If something's a 50-50 shot, right, I might think that it's less likely to happen, right, following a success. So we think about a coin, for flipping a coin, that's kind of the gambler's fallacy. If you see it come up heads, if you think that the next flip it's more likely to come up tails, you're wrong. It's still 50%, right? So their idea was, maybe some people, right, in making decisions kind of act off this, right? So they say, well, if I made this decision last time, I shouldn't make it again, right? And they're going to use 3 different types of examples to look at this. So they're going to look at judges who were giving asylum to, I think it was, I can't remember the immigration, some immigration related asylum, loan officers, and then kind of umpires, right? So we've got 3 different examples. Come down here, like I said, this is how I look at papers. I scroll through till I see a regression, right? So really what we're saying is, what's the probability that a decision is made, right? So maybe this was like the judge granting asylum. It's a 1 if they grant asylum, 0 if not. We'll look at the previous decision the judge made. So T-1 here, we're going back to the previous decision and say, okay, what was the decision that they made previously, a 0 or 1? So we can think about beta 1 here is the effect on the current outcome from whatever the previous decision was. So this would be like if the judge granted asylum to their previous case, if beta 1 is negative, that means they're less likely to grant it on the next case, right? So that would be the idea of this gambler's fallacy, where they're trying to they think if they made a decision to grant asylum, maybe, I shouldn't be making a decision to grant asylum every single time, so I might overcorrect and kind of not grant it on the next case. And it's really hard to think about. If we don't include any controls, then that doesn't really mean anything. A correlation means nothing. If we can start to include a bunch of controls so that we're comparing otherwise equal cases, right? Or if we're thinking about the loan officers, if we're comparing otherwise equal loans, right? Loans for the same amount, same credit score, start to control for all these additional factors, well, then it is interesting if we see still a significant effect here, because that's saying, even if you're looking at 2 otherwise identical cases, but one of them you previously made a decision to, approve the loan, the other one you hadn't, there's some effect that's coming from that previous decision, okay? So we kind of go back here, scroll down here, I guess. Oops. We won't focus on the streak stuff. We'll just go right to the table. So I might have scrolled too far. Where are the tables at? Here we go. So here's the first kind of example. They're kind of looking at whether or not these judges were granting asylum. Right? So they had different controls, things like the daily caseload, right? Maybe you want to control for like exhaustion, mental exhaustion, the family size of the individual that they were deciding whether or not they grant asylum to, the years since the judge had been appointed, so kind of like his experience, all these different, what time of day it was, all these different control variables, right? So when we go down here, they kind of will focus on this top row, right? This kind of final column we're not going to talk about. It's kind of some things outside of this class, or kind of outside the scope of what we're going to cover. So they provide 4 different columns here. Each one represents a separate regression, right? This lag grant, all the word lag means is it's what was the decision made previously, right? So in the previous decision, did they grant asylum or not? And the y variable that we were thinking about up there was if they grant it on the current case. Okay? So here we see some kind of negative results. Notice each column, they start to like exclude certain things. So, you know, maybe if they had, I forget the extreme judge was something like a judge who had granted very few asylums, right? So that they got rid of, they kind of got rid of them, excluded them in this column. Then they made sure that the cases were made in the same day, right? Because maybe my last case of the day doesn't have any effect on my first case the next morning, right? But cases that are like within a very similar time frame might matter more. And then kind of they even go even further and make sure that the characteristic of the cases are even more identical, right? And they don't show the results for all the other control variables. Like they don't show the results, the coefficients for like years since appointment, but all those variables are in there. So a lot of the times what these papers will do is, here we're focused on one, like we're only really interested in the coefficient on this variable, and so I'm only going to present the results for that, right? So otherwise I'd have like sometimes these really big tables and it's hard to kind of, you know, just doesn't look very appealing. It doesn't present the information very good in a good way. So kind of notice once they get all their, you know, once they get to their final kind of column here, their kind of preferred specification and preferred regression, if a judge grants asylum on the previous case, they're about, probability they grant on the next case goes down by about 0.03 or 3% less likely to grant on the following case, even controlling for all those other factors, right? Two cases where we're looking at the judge that has the same amount of experience, same caseload that day. The two families in question have the same size. Like every single one of these things, right, that we've included as a control variable is held constant. They're less likely following a granting asylum to then not grant. So I think that's fairly interesting evidence of the gambler's fallacy. Now you could probably argue here like, well, it would be nice to have a little bit more information about the exact specifics of the case, so we make sure we're comparing apples to apples. And you know, I could probably agree with you on that one. So let's look at a different example instead that maybe we think we can get a little bit more prove apples to apples here. So where's the, okay, here we go. So we've got these loan officers about whether or not they're going to kind of approve of a loan. We've got kind of different measures of the individual, you know, the loan officer, as well as, I think there's some information on, okay, so yeah, we still, yeah, so it's mostly information on kind of these loan officers, right? Their age, if they had a grad school education. Also, they kind of have these loan ratings of the loans that they were kind of looking at. So they look at this regression. Let me see, I'm going to scroll down here a little bit. Okay, here we go. And we're not going to kind of focus on a lot of the results we had here, but the one that I want to kind of look at specifically is really just this column one, right? So if I look at the lag to prove, right? So if they approve the previous loan, even with our kind of small controls that we don't have a whole lot here, but a couple controls here, looks like they're less likely, right, following a approval to then approve the next loan, right? So once again, negative correlation between the lag and the current variable. We're looking like we might have some gambler's fallacy going on, right? And they find different sizes by including different controls. I'm not sure why they could have done, you know, included several of these controls all at once, but they decided not to do that. So then the final example we'll go to, it's the same sort of idea. We've got kind of whether or not a pitch is called a strike or a ball in a baseball game. Right? So let's move down here and kind of look at, I think, what do they have here? They mentioned they have like the number of games the umpire, or no, sorry, this is just the summary statistics. Okay, so they look at kind of their controls for like outside of the two current shots, they look at like how many pitches are these umpires calling strikes or balls on average, like from their previous history. I believe they probably mentioned down here in the table. They've got a ton of, so this is the one where the other ones, maybe you don't think, they were comparing apples to apples. There wasn't as much information about the exact kind of specifics of the loan or the asylum case. But with this umpire data, they had this like, it's basically a vector, right? So like you can, there's a data set that has the vector of every pitch. So like X, Y, and Z coordinates, and you can pick up things like the acceleration, the curve. They broke the kind of strike zone down to these little 3x3 inch squares, and then said pitches that were kind of on the edge of the strike zone, right? Kind of on one of those squares that was either just inside or just outside of the strike zone. You can even control kind of for that. So it's going to be two pitches that were in the same 3x3 inch square, right? They had the same kind of speed, acceleration, all they can control for all this stuff. I mean, all these different characteristics of the pitch, as well as some of the characteristics about the umpire's like previous calls. So we've got a lot of controls here. Sorry about that. Thanks for saying something. Yeah, if that's if the audio is ever not coming through too clearly, make sure you kind of stop me. Like I said, that happens from time to time, and I have no idea why. And usually, if I retest it, it kind of goes back to normal. What was I saying? Oh, so they then kind of separated this out and said, maybe it really is these pitches that are on the edge of the strike zone that are really driving this effect. Sure enough, they find that when they look at those ambiguous, those hard to call ones, that's really where the gambler's fallacy is strongest. If they're more obvious pitches that are kind of closer to the middle or further outside the strike zone, looks like, the effect is a lot smaller, right? 0.002 instead of 0.03 here. So I don't know, I thought this was an interesting paper. We talked about kind of the gambler's fallacy a little bit in class and the hot hand fallacy. So this is a paper where they took 3 different real world examples, and really the way that you would test whether or not the gambler's fallacy exists, all the way back up, is really just look at whatever variable you're interested in, the current outcome, and then include as an X variable your previous outcome of that variable, right? So, whether it was a strike or not, whether the previous pitch was called a strike or not, whether or not you approve the loan or not, whether or not the previous loan was approved, kind of that's how we would kind of estimate to see if there's gambler's fallacies that exist in really any scenario where we have like decision making like this going on. Okay, so I like those 2 papers, but I want to play around with some Excel stuff. I don't know if I really like this example as much, but I think it's we want to kind of get a look at how we do these things in Excel and how we evaluate some of the output that we'll see from Excel. Okay. So I put this powerlifting small data set up on Canvas. We're going to look at sheet 2 here. So there's sheet 1 and sheet 2. We'll look at sheet 2. And we've got all these different variables. I'm going to zoom in so we can see them just a little bit better here. So we've got, the meet ID, the name of the lifter, their body weight, age, an indicator or a dummy variable for 1 if they're male, 0 if not. These raw and wraps are just different, how would I say, different tool or, different things that the lifters can use. So raw is they can't really use kind of these this equipment that helps them lift more. Wraps is a little bit of an assistant, and then the one that's not included would be kind of this fully assisted lift where they're using things to help make them be able to lift quite a bit more, right? So those are just things that we should be controlling for. I've got the age squared variable in here, so we'll kind of have a small discussion about what happens if we have nonlinear relationships as well. And I then have, so these are kind of my control variables I was thinking of. And then here we've got different measures of kind of what the weight was that was lifted in these powerlifting meets. So we've got the total weight lifted over here all the way on the right. their best deadlift, bench, and squat, their per pound weight lifted, and then something called the Wilks, which is essentially trying to capture this per pound, right? How much you lifted per pound of your body weight. Okay. So one thing I think, I think we won't have a clear answer, or at least by the time we get to the end, we're going to run into a problem where we see an estimate and we're probably thinking, we have to remember it's just a correlation. We've got to be careful really interpreting these as causal, especially when we don't have a lot of controls that we might think are really, might influence the Y variable. So the very first thing I'll do is we'll go to data. Hopefully you've all been able to add. I haven't heard anyone I've heard from that has had trouble with it. We've got that worked out. So I haven't heard from anyone and not been able to solve anyone getting this data analysis added in. So we'll click on data analysis. We'll then come down here to regression, hit OK. So the Y variable we're going to look at is this total kilograms lifted, right? So I'm just going to select that total kilograms lifted variable. The X variables that I want, right? I'm eventually going to want all of them, but I want to show you kind of one thing first. So we're first going to start out, maybe we just think, I don't know, gender matters a lot in this example, right? So maybe I just look and see, okay, what's the effect of being male on kind of weight lifted? I hit okay. Looks like it's a huge effect, right? P-values are 0 because we've got 86,000 observations, and we're explaining 50% of the variation. Now, the problem is, right, we've omitted a lot of other things that matter. And one thing that well, I shouldn't say we know it, but if we look at other sources, we can pretty quickly determine that the average weight for males just in general is much higher than females. And specifically, it's probably going to be quite a bit higher when we're looking at individuals who are kind of performing these at these powerlifting meets. So we want to control for their body weight, right? So let's just control for their body weight and age here. Excuse me, so we'll go same Y variable. The X variables now we want our body weight. And actually, I want to go through a little bit of a discussion of something else. So I'm going to actually move this around first because I only want to include body weight. I'll wait and include age later. So I'm going to go, that Y variable is still total kilograms lifted. I want the body weight and the male variable, so I select those. I'm going to run this regression. Okay? So we'll hit run and we'll move this over here. But if we look back at this output, right? One thing that we had from last class was that we had this bias component, right? So the bias of our estimate was going to be, so if we had, call it B hat is equal to, let's go to, B hat was the B hat, call this 1 for whatever the first variable we're looking at, was the actual, no, not B hat, sorry, was the actual relationship between that first variable and the Y variable. But then we had this additional bias component, which was the effect that variable that you left out would have had on the Y variable times the covariance between x1 and x2 divided by the variance of x1. Now, we don't really have to worry about this because it's always going to be positive, this variance component. So we want to try to figure out in what direction will this estimate be biased, okay? So we've kind of got that. I'm going to, once again, zoom in so we can see things a little bit better. All right. So the thing that I observe from the Excel output is B hat, right? So I observed 275 there, right, on that male variable. Now, that captures the true effect, but also this additional component. So if I then, in my next regression, include x2, which our x2 was body weight, right? What effect do we think body weight is going to have on the amount someone can lift? This is probably positive. What's the kind of correlation, the covariance between kind of this gender variable male and body weight? Well, that's probably positive as well, right? If an individual is a male, it's likely that their body weight's higher. So we're going to have a positive bias here. So when we see 275, a part of that is coming from this bias component. So then when I include x2 in my regression, that will eliminate that bias, so I should see a smaller estimate now. So sure enough, if I go to the regression output when I included body weight, right, notice it's fallen from 275 to 196. Right, so quite a bit lower, and it looks like body weight has a significant effect. Right? All these p-values are 0, so we can say that all of these estimates are significant at the 10, 5, and 1% levels. We're now up to explaining about 65%, right? The R squared, we're explaining about 65% of the variation in the amount of weight that's lifted just by these two variables, so already up pretty high. Okay. Now, eventually what we want to do, I was just kind of using that to make the point that there is a difference, right, between, or trying to give you an explanation of the bias that exists and the difference between those two estimates from kind of a simple linear regression to then the one where we added in an additional control variable. All right, I'm also going to move this around just so it's easier for us to see. And now we're going to go to data analysis, and now we're just going to include, so same total weight lifted. We're going to include everything, right? We're going to go from age all the way to this wraps variable. Okay. So hit OK. We'll get this kind of final one. So notice here, p-value is still really close to 0 because we've just got so many observations. But now we'll look at something we haven't talked about for a hot second. So we're up, our R squared is up to 7.73. So, you know, explaining 73% of the variation in this total kilograms lifted, or this Y variable. So what I now want to look at, right, is this age and age squared variable. Okay. So maybe I think the amount of weight that someone's lifts, I actually don't know ahead of time, but I would have imagined it probably increases with age, but there's a point at which it stops increasing, right? And so if we think about, we had a discussion about this where it's really thinking about it as a quadratic equation. So we've got kind of, get this written in here. Now I'm just going to put in, we had other variables, but kind of the two that we're really just focusing on here are this age and this age and age squared variable, right? So what we're thinking about is we've got age and kind of the kilograms lifted here. That as someone's getting older, that starts to increase, but it increases at a decreasing rate, right? To where eventually, potentially, there's an age at which it then would start to then decrease. So we're probably thinking, so in this scenario, right, it's increasing, so that first coefficient will be positive, but at a decreasing rate, so we would expect that second coefficient to be negative. We can see if that's true, and actually run that. We had that regression ran, so we look here, sure enough, it's increasing, right? That coefficient on just the regular, non-squared variable age is 11, but our age squared variable, right, that coefficient is negative. So we've got a situation where the relationship between the x and y variable, it's increasing at a decreasing rate. If that's the case, we expect a positive coefficient on the non-squared x variable and then a negative on the squared. What if I had it increasing at an increasing rate? Then I would expect a positive and a positive. So that's a good example of kind of how we can look at these nonlinear relationships. And so our male variable that we originally started with didn't change much, but I kind of thought this was like interesting. I still think, we'll return to the discussion. Notice, it went from 274 to 196 when we just include the body weight, right? Well, I've always had this idea that I would love to do, and I think I kind of gave you guys a snapshot of it earlier in the semester where I don't know. I think that, muscle tissue is muscle tissue. So it's like, and then like, we're all like our skin cell, everything's the same, right? So if someone weighs the exact same amount and maybe had the exact same stature, I really don't, there's no reason maybe to believe that there'd be huge differences across the genders. So, just including the weight, you can see what looks like is a positive effect falls quite a bit. So if we had like height, right, and we could throw that in there, right, we could probably like get that weight, even lower. We don't have a lot of extra data here, but what we can do is I'm looking at this total kilograms lifted, right? But maybe I should be focused on something more like per pound lifted, right? Now this actually we'll do the Wilks score. I think it's kind of the same idea, but the numbers are a little bit bigger, so we can kind of see this play out. So I'm gonna look at instead my y variable being this Wilks score, which tries to kind of capture, right, or make sure you're comparing kind of otherwise two similar individuals, right, in the same kind of weight class and things. So we'll include all of our x variables again, kind of see what the effect is here, and kind of we still have a significant effect here, and it's positive, but the Wilks kind of being larger, similar to like total kilograms lifted, we don't see quite the decrease, right? So I think just us showing that bias existed when we went from male and then included body weight, if we had additional components like height, I always thought that would be really cool to see, like, if that effect actually goes down to zero. My guess is that it would, but alas, we are slaves to kind of whatever data we have. We can't really create variables, right? If they don't exist in our data set. So I thought I wanted to make sure we had the discussion about the nonlinear relationships, revisit this kind of idea of the bias that exists in our estimates, see how we go through this in Excel. This was a pretty easy one because with this many observations, right, we can reject the null for all these variables because the p-values are always basically zero, right? Just to and kind of we revisited the discussion of what the r squared means. You can kind of see as we add in additional control variables, we were able to increase that r squared, right? So if we kind of look backwards, we went from 0.73, 0.65 to the very simple linear regression, we only had 0.53, right? So you can kind of see as we add in additional control variables, we're increasing that r squared, right? Any questions for me on any of that? Okay. All right. So I also I think I mentioned this Monday, and I tried to show you how to use it, but I did get that figure your grade tool posted. It has the kind of individual grades or individual assignment grade as opposed to the one that I was showing you, which was for a different class. It's got the exams weighted appropriately for this class. The final exam I posted, I was gonna say, final exam practice materials. So there's just one up there right now, and kind of, I put a formula sheet, although a lot of what it's gonna be is working with this regression output, making interpretations. I think that final connect assignment, some of those questions probably will help a little bit also to kind of revisit those and study for the final. I'll get some additional questions posted before Friday as well, before the end of this Friday. But for now, we can kind of start looking at these, and these will be the ones that we're reviewing next week as well, okay? Any other questions from me before we probably end class a little bit early here today? More information. Yeah, so I'll post next week, at the beginning of the week, more information on the final, but it's going to be, I'm going to post it the Monday of finals week, which I think is the 14th. And then it'll be open that Monday, Tuesday, and Wednesday. All right, so you can take it at any point at one of those days, and once you start, you have a certain amount of time to finish. I'm still, kind of fine tuning it based off of discussions that we're kind of having this week. And after this weekend, I should have a better idea of exactly how long you'll have to take it, how many questions there will be, exactly. But yeah, it'll be similar in length, I think, to the other exams. It will be. I will be. A lot of it's just going to be looking at regression output. Like I'm not going to have you run a regression like you would for the Connect homeworks, but I'll show you Excel output, and then kind of ask you questions about different things that we've been talking about. What's the best interpretation of R²? There might be a little bit more short answer on this last one than there is on than there were on the first two. But other than that, it should be fairly similar. Any other questions for out here today? Okay. I guess I also should mention, right, your last individual, that third individual assignment is due at the end. That's set for 7th. Oh, never mind. I was going to say it's due on Friday, but I guess I have it set for being due next Monday. So you got a little more time to work on that if you really want to. I jumped the gun a little bit on that. Any other questions for me before we kind of go on here? Oh, I know what it was. The Connect assignment is due at the end of the day, Friday. So make sure you get that Connect assignment done. Try to get that individual assignment done as well. I think because we're remote, where we're at, those are going to be the last assignments. So I'll start also after those get turned in, kind of giving you a better idea of exactly where you're standing in the class, so that you really, the only thing left should be that final exam score, right? Once we get those graded. Yeah, I'll probably still drop the lowest. We ended up not having quite as many individual or kind of Excel assignments, but yeah, I'll end up kind of dropping the lowest there. So I mean, technically, if you've already done the first two and you're happy with your grade, you don't have to do the third one. Or if you're happy with your first 3 connects, you don't have to do the fourth. Now, that being said, I would highly suggest working on those assignments and as at least at the very least study tools for the final. But yeah, I still will be dropping those, but those aren't reflected yet. So I'll wait till everything's turned in until I kind of drop those and show you what your grade is with the lowest drop. Any other questions? These are good questions. So what should we put as our iClicker grade? Oh, it should be here. I have to to a student view so I don't show everyone's grades. Let's go to student view. Okay, so when you go to grades, just scroll down here. So we've got kind of the Excel, Connect, individual assignments, and then here it's got your highest and lowest exam. So it already tells you your highest and lowest. So doesn't really matter. You could enter these in as exam 1 and 2, or you could go up and grab your actual exam 1 and 2 grade. Either way, as long as you're putting that into your figure out my grade tool in that exam 1 and exam 2 slot, then that calculator kind of thing should work fine. So whatever score it has here for online quiz, whatever percent it gives you, that's what you'll be using, right? So when you look at online quiz, Excel, Connect, and individual, those will be the percentages that you plug in to that Excel file that, oh gosh, let me see if I can get out here. Let me go back to Canvas. All right. So those will be what you plug into these first 4 columns. And like I said, whatever those 2 exam scores are, it doesn't matter which order, even if you mix up exam 1 and 2, just enter those 2 exam scores in here, and then you can kind of play around with the final to see what grade you'll get, right? Does that answer the question? Now, if you're having, okay, any other questions before we kind of call it today? Okay, so I'll be doing like last kind of final news, I guess, new stuff On Friday, it'll just be linear regression. We'll probably revisit the idea of using multiple dummy variables because we haven't talked about that in a hot second. I might do a little bit more review of the log specifications, just seeing things in different, different types of examples, but no real new information, just seeing it presented from different topics. Okay. All right, there's no more questions. I will see you guys on Friday.